In this module, we start looking at numerical data types in C++, and we look at how important it is to be at least aware of their characteristics and limitations. The focus on this presentation is on integers, and we'll just give a sense of how the processing of integers happens on a computer and how C++ expose the different types to the user so they can have control over the calculations, with particular emphasis on the limit cases and what situation, for example, that people would call overflow or change of sign and things like that. So there are different representation depending on number of bytes and so the range of value. There are different ways of representing the numbers in a way that can be friendly to both humans and machines. In particular, the hexadecimal is kind of the place where the two to some degree meet together. And then we'll look at how the limits of those numbers can lead to overflow of conversion can be wrong. And at the end I'll show a brief video just to highlight how issues like this that seems really to be picky on small details can actually lead to fairly dramatic results. Integers, and we'll talk about floats in another module. Integers can be represented by different number of bytes. The most common type int can be formed into 32 bits, which is 4 bytes, and if in that case the range of value, so if it's signed, the range of value would be from -2 to the 31 to 2 to the 31 minus 1. Notice the asymmetric structure. There is basically an extra negative number because 0 that effectively is neither positive or negative practically in a computer is treated as a positive number, and this is derived from the fact that one of the bits is used as a sign, and so the sign of 0 is the same sign as any positive number. Unsigned numbers don't have this asymmetry, so for example if we have an unsigned 32-bit integer, it ranges from 0 to 2 to the 32 minus 1. Notice that the exponent here is different by 1. Shorts are similar, just that they have half of the bits, or basically 2 bytes instead of 4. And so they symmetrically have signed and unsigned version, while long depends on declaring something simply as long may actually have an unpredictable result because they depend on the compiler. Effectively, on a 32-bit machine, they would still remain 32-bit integers, while on a 64-bit they would be 64 bits. Long, so we'll double in the definition, should be guaranteed to be 64 bits. In general, there are ways to determine the size of a type, and so the results of such request, the function would be size of, gets stored in this in an object of type size t, which is effectively an unsigned integer of type big enough to contain the number of bytes of the largest possible memory representation, but effectively it's a positive, so unsigned integer, and so if I do size of an int, this will give, for example, store a number 4 in an object of type size t, and if it's a long, the result would be 8 number of bytes. C++11 provides a set of types that kind of clear the air from this potential confusion. And so instead of just call things ints, floats, and so on, there is a specific indication of the number of bits used. And so every byte is 8 bits. So an int 8 t, it's an integer made of a single byte. Int 16, int 32, int 64, those are all signed integers. And the uint, which stands for unsigned int, and those are the same type but without sign. And so those types are effectively safer to be used whenever the precise size and storage of those types it's of consequence to a particular application. So let's look at how numbers are represented. So here I'll show different way of counting. So first of all, decimals is basically what we normally use for representation. And we know that the basis 10 really derives from the fact that we have 10 fingers. But the key is that you have 10 symbols, 0, 1 to 9. And then when you run out of symbols, you go back to 0 and add in the next column a 1. And then you start going through the numbers again. And then when you go to 19, you go to 0 and so on. Now, while the number of symbols can change, the technique of counting is effectively the same. It's just that you run out of symbols at different numbers. Given that a computer uses the binary system, so it's easier to compare numbers kind of from a human understandable system to binary if the number of symbols is a power of 2. For example, so here, first of all, let's look at how we would count in binary. So number 0, let's say that we have 4 bits. So number 0 would be 0, 0, 0. Here we're thinking without sign. And then number 1 is 0, 0, 1. Now in binary now we already have ran out of symbols. And so when we add 1, we kind of carry over. And then we go back to 0. So you get 0, 0, 1, 0. Then we add 1 again, and you have 0, 0, 1, 1. At this point, again, adding 1, we have run out of symbols in 0, 1. Then we go to 0, and we add to the next column, and so it becomes 0, 1, 0, 0. Now here we go through the same sequence of 4, just with the 1. And then we go through those 8 symbols, but now with 1 in front. And so, again, the mechanism is the same, but given that a computer understands best binary, this becomes excessively verbose for humans. And so there has been developed in the past a couple of options. One is to use 8 symbols from 0 to 7. And so this would be the octal system. And effectively you run out of symbol so there is an alignment. Basically you run out of symbols after 8 stages, so then they both get an extra 1 in this position every 8 steps when you keep adding by 1. A slightly better approach is the hex approach, where you have 16 symbols. And the reason why it's better is that you have alignment not only at the time where we increase the number of digits, but also the fact that in hexadecimal approach we actually have all the 16 symbols that you can run through with 4 bits. And so for a full byte you would need exactly 2 hexadecimal symbols, while in octal there is still a misalignment with respect to using a byte or not. So traditionally the 16 symbols is from 0 to 9 and then A, B, C, D, E, F. And so if we were to do the number 16 in hexadecimal, there would be 1 and then 0 that would correspond to 16, which in the binary then would be 1, 0, 0, 0, 0. Now, obviously, it's not very important to remember everything in detail, but it's important to know the concept so that whenever this is of a consequence, for example, if you go and you have to debug a problem and you have to look at the numbers in the computer, the debugger can show you sometime in decimal if that's good enough, but sometime in hexadecimal as a proxy for the binary. So now let's look at how computation works in binary. And again, the idea is that they work in a way that is kind of similar to the traditional approach. For example, if I have 0, 1, 0, 1 added to 0, 1, 0, so we will have 1 plus 0 is 1, so 0 plus 1 again is 1, 1 plus 0 is 1, and 0 plus 0 is 0. Now this is the simplest form of addition because there was never a carryover of any type. Now if we have a number like this where we have 1, 1, 1, 1, and then we add 0, 0, 1, based on the fact that we only have two symbols, 1 plus 1 would be 2, which is really 1, 0 in binary. So we would write 0 and carry 1 at the top. And so then we have again 1 plus 1 plus 0 is 1, 0. So we write 0 and then we carry over another 1 in the next column. The same way we would do in decimal, but you have to get to 10, not to 2. 1 plus 1 plus 0 again is 1, 0, and then we carry over error 1. 1 plus 1 plus 0 is 0, and then we carry over another 1. So as you can see, we start with two numbers that use 4 bits each, and we do a calculation and we end up with 5 bits. Now, this is fairly standard. The only problem is that in a computer, you don't make the assumption that we do normally as humans, that in principle you can keep adding symbols in front, so you cannot have infinite precisions in your numbers. But a number may be formed out of 4 bits or 8 bits exactly, and so at some point this operation of just adding an extra bit is not really allowed, and some unpredictable event may happen. So, for example, let's look at an addition with signed numbers. So now things get more tricky. So first of all, the convention is that the first bit, the bit on the left, it's the sign of the number. So 0 will mean that the number is positive, and 1 the number is negative. Now if we do the traditional addition, here what we have is like 1 plus 1 is 0 and we carry over 1, so here we carry 1. 1 plus 0 plus 1 is 1, 0, and we carry over 1 again. And now 1 plus 1 plus 1 is 3, so this will be 1, 1, and so we have 1 and 1. Now, if those were a positive number, we would have had a proper addition, 5 plus 7 equal 12. The problem is that this is a signed number, and so 1, 1, 0, 0 actually is minus 4, and so this leads to a mistake, that if we do the addition kind of in a traditional way, we have run out of precision and we add two positive numbers and we have a result that is negative. Obviously, if this were unsigned numbers, so we didn't use the first digit, a binary digit, as a sign, we would have a proper addition 5 plus 7 equal 12. And so here we can start seeing how things can go wrong in this space. So similar example. So we add now two negative numbers, and of course we would expect the results to be a negative number. So, but then we do addition in traditional way. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. But then 1 plus 1 equal 1, 0, right? And so here there is an extra bit, but it gets lost. And so we get 0, 1, 1, 0, because we only have 4 digits, and so the additional carryover cannot be stored. And so we do the addition of two negative numbers, which obviously should lead to a negative number, but because the first bit is the sign, we would get the wrong result in a double way, because it's the wrong absolute number and the sign is wrong. So if this was unsigned and we have the additional bit, then this would be a 12 plus 10, 22. But again, even in this case, given that we do not have this extra bit, we have 12 plus 10 equals 6. So in this case, we get a wrong result. In the first case, you have two negatives that become positive. In the second interpretation, even as an unsigned, we add two positive. We have what people would call an overflow, and though you get the result that is smaller than the two original numbers, so clearly it cannot be a result of this addition, so things are not working properly. So this is a type of errors that one always have to watch out for, and we'll provide a simple exercise to make sure people can understand this, and we'll also provide a class based on actual code. But I would like to leave you with a thought of what are the consequences of calculating and not being careful with things like this. For example, if you design a space vehicle that is all built by a simulation without testing, which was done, and in fact tends to be more and more frequently, how important is that these tiny details are being taken care of. So this is the example of the Ariane 5 first flight. This is 1996. And as you can see, the result is fairly...
37 seconds into the launch, the onboard computers decided 501 was 90 degrees off course.
So, well, first of all, fortunately this was not, there were no human on this rocket, so that's the good news. But still, it's think about it, this is a project that cost $370 million, and in 37 seconds, basically we're talking about 10 millions per second got lost and destroyed. Although, as you can imagine, for a space mission like this, there was a large team of software engineering designing everything. So what went wrong? They did an analysis of the whole system. Have you seen that the trajectory kind of turned suddenly? And the interesting results was that there was a software bug. My understanding is actually they were using this library with short integers for efficiency reason, and the library actually has been tested for a long time in the previous Ariane 4 mission. So it was understood the library that it was very robust, except that the input was given by some new way of building the input information from 64-bit floating point numbers that were fed into those 16-bit signed integers. And the assumption that in previous mission was true, that the range of value was always valid for the 16-bit, was now actually beyond the 16-bit capacity. And you had something very similar to what we've seen in the cases before, where things would go overflow, and for example, the sign of a number could change. In this case, it was an angle, so there would be a rotation and things would go wrong. So this to illustrate those are just not like small picky details. It's very easy to have very difficult bugs to find hidden in the portion of the code that use integer values or other numerical values without the particular verification and control. And so in the next module, we'll look at the case of floating point numbers again, and we'll provide now a companion module where we go through code and show how the use of integer is important in this way. Thank you.